Hello, my name is Abby Carroll and today I will be looking at whether derbies are different by looking at my statistical model for predicting football outcomes in the Premiership League. This video is intended for a general audience who has an interest in Premiership League football with a knowledge of basic statistics. In this presentation, we'll briefly look at how I created and developed my model and then the comparison of this model to derbies in particular. The objectives of my project were to create and develop a successful model that predicts outcomes of football games in the Premiership League more accurately than if we were to simply predict a home win for all games. Then to compare the predictions from the model against what we observe for derby games in order to evaluate whether they are different from normal games. My motivations for conducting this project are that football is the most popular sport in the world, resulting in the existence of many online websites where you can join a team or mini-league to compete against your friends or other people from around the world to predict the most outcomes correctly. I am also interested in the widely held belief that is associated with derbies that playing a derby affects the outcome of a game. This is an understandable belief because they are classed as high-profile games, so there is a difference in the mentality of the crowd, which would therefore affect the performance of both the players and the referees. I retrieved all of my historical data from football data and used the 2002 to 2013 data to create the model, meaning I used 4,180 previous results. I then checked the accuracy of the model against the 380 games I retrieved for the 2013-14 season. The raw data shows us that a home win occurs 47% of the time, an away win occurs 27% of the time, and a draw occurs 26% of the time, and so my model needs to have a higher percentage accuracy rate than 47%. I then needed to objectively rank a team in order to create the model. Football data states, a rating system provides a quantitative measure of the superiority of one football team over their opposition in a match. However, there are many ways in which we can do this. I initially wanted to look at the simple ways of doing this purely based on the outcome of previous matches, and so I decided to look at using the goal differences and then the points differences for previous games. I first ranked my teams using match ratings, which incorporates the goal difference from previous games. However, I needed to decide how many previous results we should use in order to create the most accurate model, and so I decided to look at the previous 1 game up to the previous 6 games. This resulted in calculating a total of 6 different match rating models. To calculate the match rating for the home team, we first needed the goal superiority rating for the previous n games, where n is dependent upon which MRN we are calculating. To calculate the GSR for the home team for the previous game, we subtract the away team number of goals from the home team number of goals in the match. We then repeat this process for the away team. Once we have calculated the GSR for the previous n games for both teams, we then sum these for each team and subtract the away team's GSR from the home team's GSR in order to calculate the match ratings for that model. I then ranked my teams using points ratings, which incorporates the previous points received in the last n games, where a win is worth 3 points, a draw is worth 1 point, and a loss is worth 0 points. The calculation for this is the sum of the previous points received in n games by the home team, minus the sum of the previous points received in n games by the away team. We then calculated the probabilities of each outcome for each match rating and point rating being observed from the raw data using the calculation. Probability of a home win is equal to the number of home wins divided by the total number of games, with a similar calculation used for the probability of an away win and a draw. However, we need to incorporate the uncertainties of each of these outcomes by using the calculation. Uncertainties is equal to 1 divided by the square root of the number of games. We then need to use these uncertainties to calculate how these propagate onto the individual percentages by using the uncertainties of a home win divided by the number of home wins all squared, plus the uncertainties for all games divided by the number of games all squared, with similar calculations for an away win and a draw. This means that we can see the chances of the model being incorrect for each match rating or points rating. We would expect the errors to be largest at the extreme match rating values, as there is less data to base the model on, and likewise for the points ratings. The scatter graph shows us the observed probabilities for home wins, away wins and draws, with both relative first order fits in solid lines and second order fits in dashed lines in blue, orange and grey respectively, for the 2002 to 2013 MR6 data. This displays how the two different order of fits do in fact give similar results. These fits are effectively our models, in that we apply the equations to the match ratings for each game, and whichever probability is the highest is the outcome we pick. We can instantly see that a draw is never the most likely result for both fits, and found that all of the models were similar in that the intersections were on the negative side of the ratings. We can note that the point ratings plots do differ from the match rating plots, as their range is smaller, as the maximum points per game is 3, whereas goals are unlimited. We have also seen that, as expected, the error bars are the largest for the extreme values. I then compared the accuracy of each match rating and points rating model at predicting the outcome of a game by applying the equations to the 2013-14 data. This shows us that for some of the MRN there is a difference in accuracy when using a first order fit compared to a second order fit. However, we can see that overall the match rating with the highest accuracy percentage is MR6, which was 51% accurate for both fits. The highest percentage of accuracy was found for the first order PR6 being 52% overall. I then conducted 5 goodness of fit tests in order to check the quality of the models. The tests I conducted were the R-squared test, the adjusted R-squared test, the S-statistic, the chi-squared test, and the reduced chi-squared test. The results of these tests showed that the best first order fit to use is MR6 and MR2 is the best second order fit to use for the match ratings. And the best first order fit to use is PR1 and the best second order fit is PR2 for the points ratings. When doing this, we saw that for the MRN, where n is an odd number, the models resulted with lower goodness of fits compared to when n is an even number. This suggests that the model is highly affected by having an uneven amount of home games and away games involved, as we found that the majority of games are played home and away consecutively. If we compare the accuracy of the first order MR6 and PR1 model, second order MR2 and PR2 model for the 2013-14 data, we saw that the first order MR6 model has the highest accuracy percentage of 51%. When we compare the results using the historical data from 2002 to 2013, we can see that the first order MR6 model also gives the highest prediction accuracy. The goodness of fit test showed that the second order MR2 model has the best fit. Therefore, I used the first order MR6 alongside the second order MR2 models for the rest of my project, as overall they are slightly more accurate when taking into account the actual results we found and the goodness of fit tests. In order to incorporate the abilities of each team, I then looked at the difference in the previous season's league position against match ratings. Due to the clear difference we can see between the positive difference in league position and the negative difference in league position, I decided to split the dataset to create smaller models. We did not use 0 in this, as this occurred when the teams had been newly promoted to the league. For the positive delta league positions, we managed to increase the accuracy to 64% when applying the model to the 2013-14 data. When we separated these into smaller bins, we managed to increase the accuracy percentage to over 90% when we looked at the extreme positive delta league positions, which is what we would expect. For the negative delta league positions, we can see that this is where the model struggles to give correct predictions, as the overall prediction accuracy decreases to 46%. By doing this, we can see where the accuracy of the model is more likely to be true, therefore suggesting that we can use our judgment for when to apply the model successfully. In order to see whether derbies do indeed behave differently to normal games in respect of the outcome of the game, I looked at the comparison of the observed probabilities of the derbies against the predicted result from my model. From researching derbies, it is clear that there are multiple variations of what is classed as a derby within the Premiership League. I therefore tested 3 different definitions of derbies in order to see what impact this has on the model. The 3 definitions I used were sourced from Kent 2015, Football Manager 2015, and Football Derbies 2015. I then went on to create a derby set based on distances from each of the home grounds being 20 miles or less. The first identifiable issue we have when looking at derbies is that the amount of data we have to use severely decreases down to between 100 games and 502 games. Out of the previous 4,180 games we had available, this is only a very small fraction. Due to the decrease in data, I decided to look at the MR2 first order model that I have created. To see whether derbies behaved in the way our model predicts, I plotted our predicted probabilities using the model against our observed probabilities from the initial set of derby data. When we looked at the plots for home wins, we can see that derbies do not behave in the way we would expect, as seen in the scatter graph. The orange line shows the 1-to-1 ratio line, with a linear fit for the comparison shown in blue. As we can see, the probabilities are not equal and actually show a negative correlation. This suggests that the initial set of derbies do indeed behave differently to normal games. However, we can see that the majority of the error lines do in fact cross over the 1-to-1 ratio line, which did not improve for any of the definitions of the derbies I sourced. This means that there is in fact scope for derbies to behave normally. Then, when looking at the probability of an away win, this gave us the same result, in that derbies do not behave like normal games do. However, we cannot be certain how much so, due to the error bars showing that there is scope for derbies to behave normally. When we are looking at draws, we can instantly see that draws behave in a unique way, in that the predicted values are all very similar to each other due to the gradient of the prediction formula being very small. For example, for the first set of derbies, the gradient of the prediction formula was only 0.003. This meant that all the probabilities were within 0.1 of each other, whereas our observed values ranged from 0 to 1. We can speculate that this is due to the limited number of games that we are using from the historical data, and identifies that predicting a draw is still a problem within derbies. We did find, though, that these error bars did not cross over the 1-to-1 ratio line as often for the distance-based derbies for both home and away wins, therefore strongly suggesting that this set of distance-based derbies do not behave like normal games do, and so needs to be taken into special consideration when we are using our prediction model. Overall, we have seen that it is possible to create a model that predicts the outcome of football games in the Premiership League. We have seen that by using all of the historical data from 2002 to 2013, we can successfully create a model that is 51% accurate, which is higher than if we were to predict a home win for every game. This level of accuracy can also be increased up to and above 64% if we set parameters on the difference in league position, which indicates the ability level of the home team. We have also found that derbies are indeed different to normal games, however, to what extent is not known. This therefore suggests that these games need to be taken into special consideration when we are implementing the model. The distance of each team's home ground from one another has a more significant difference when we are comparing the probabilities, suggesting that this model could be developed to incorporate this. From my findings, it is clear to see that modelling results based on the differences between home grounds could make a significant difference on the accuracy of the prediction of outcomes, and it is therefore worth developing the original model so that it incorporates the distance within it. We have also used a very basic method of separating the abilities of each team, and so the model could use more statistical data for each of the teams to include a true indicator of each team's ability levels in the games. Finally, I would like to thank my project supervisor, Dr. Dan Smith, for his support and guidance throughout this project. For further information, please refer to my paper, Are Derbies Different? A look at statistical models for predicting football outcomes in the Premiership League. Thank you very much for watching.